All right, taking a look together at 443. Looking at area under the curve still. Getting a little further. So Adam, Becky, and Kathy were working on finding the area bound by these three curves. And we've got it shaded in our graph, of course. And they've got three different strategies. Yesterday in class, I think Adam's strategy is the one that we're all familiar with. Adam says I'm going to use vertical rectangles, and I'm going to do top minus bottom. Now, what does Adam have to do? Similar to yesterday, area bound by three curves. The bottom actually changes. So he's got to find his intersections, of course. And this one is 0, 9. This one algebraically is 1, 1. And this one ends up being 3, 9. So Adam says, well, let's do the integral from 0 to 1 to find this area right here. The top curve is y equals 9 minus the bottom curve, in this case, was the negative 8x plus 9. Plus the second part of the curve is over here, has the same top curve, 9. Now our bounds are going to be from 1 to 3 on this one. And the bottom changes to x squared dx. So a little algebra simplifying. 9 plus 8x minus 9. We can probably just rewrite that as 8x dx, which is convenient. Plus from 1 to 3. This one's already simplified. So let's antiderive. 8x squared divided by 2 from 0 to 1. 9x minus x cubed over 3 from 1 to 3. So if I put the 1 in here, I get 8 halves, which is 4. If I put the 0 in here, I get 0. Plus, let's put the 3 in here. And that ends up being 18 minus 8 2/3. So my answer there is going to be 4 plus 9 2/3. So I think we're going to get 13 2/3 using Adam's method, which is the method we've been practicing in class. But let's check out Becky and Kathy. Maybe there's an easier way. According to Becky's drawing, she's got another way of thinking about it. She drew her rectangle this way. So now let's talk about the dimensions of her rectangle. She's going to have an x value and an x value for her height. Instead of a y minus y, she's going to have an x minus x. So what are we going to have to do? What if we labeled this curve in terms of x? So in this one, x equals square root of y. In this curve, I guess we're not going to use that one, are we? In this curve, what would x equal? If we redo this one, it's going to be y minus 9 over negative 8 equals x. We got that? So what's the height of our rectangle, or length? That's this x value minus this x value. So this x value is the square root of y, that's what x equals, minus this x value, that would be the height. What's the width? Well, in this case, it's the change in y. Now, could we do an integration here? What would we integrate from if we're integrating y's? Her rectangles would all go like this. So where would they go from? They would go from 1 to 9. Can we put that in our calculator and see what that value would be? We've integrated, we can integrate anything. We can integrate from 1 to 2 of a dA. Letters don't matter in here. We can change letters all we want. We could pretend these were x's if we wanted. But in this case, they're definitely y's because we're going this direction. The convenient thing I think about Becky's is that we only have one integral. In Adams, it wasn't a problem. We did 2 integrals. But it's kind of convenient just to do 1. And what would you describe as happening in Kathy's method? It looks as though we've still got our 3 curves. It's definitely representing the same area. And she's back to going vertical. But what has she changed? It looks like she's reflected it over the line y equals x. So if she's reflected it over the line y equals x, she's actually kind of done the inverse stuff, hasn't she? So this is going to be y equals square root of x. This is going to be x equals 9. I can see that right here. And then this is going to be y equals x minus 9 over negative 8. So now, this is convenient because, again, we've only got one top curve and one bottom curve. We just stop at 9. So our integral from 1 to 9 of top curve minus bottom curve. That actually looks a lot like Becky's, except for we changed the letters. What does that show us? I think that shows us that we can manipulate equations and find the same values. We could integrate this by hand. Let's put that in our calculator, see if we get the same answer.